Hi class, it's Mr. Hofstad here with lesson 5 of unit 6 on mechanical waves and this really important universal wave equation. You will actually recover this in Physics 30 if you take Physics 30 because it is so important. So let's get into it and kind of go over the definitions first. So a mechanical wave is, as we talked about in our first lesson of the unit, a wave that requires a medium to travel through. So it's all types of waves other than electromagnetic radiation, which doesn't require a medium. These mechanical waves can't travel through a vacuum, right? They're vibrations in some medium that we're going to focus on today. So when there's a regular source vibration, right, it could look like something like this, right? That could be the particles in a bell vibrating. That's not a very good one because we'll see that sound is a little different. Let's say this is somebody holding onto a giant slinky and swinging it up and down, vibrating it, and creating these waves as they travel through our slinky. So whenever there's a regular source vibration, the energy created travels through the medium in the form of a wave train. And kind of see where that idea of a train comes from, right? They're all connected to one another, almost like a train would be connected to the other cars in the train, right? And it's got this kind of chain effect to it as well. And that causes the particles to move in simple harmonic motion. So this is why Unit 6 is both simple harmonic motion and waves, because waves do demonstrate a lot of properties of simple harmonic motion, especially when we start looking at individual particles in our wave train. So we've got two types of mechanical waves. The first is transverse, and these are our ideal ones. These are the easiest ones for us to visualize and work with. And they're whenever the source vibration occurs perpendicular to the wave train motion. So here we have the wave motion, right? So if we imagine the wave starting here, it's going to move to the right, up and down. It's a little bit tricky to see just as a still image. When you watch videos of this, it becomes a lot easier. The first video I posted from Crash Course in our last week's material has some good visuals of this. So our source vibration is up and down, and our wave motion is to the right. So that source vibration is perpendicular to the wave motion. And here's again a recap of the vocabulary that we're going to be using with waves. The crest will always be the highest point, so it'll be one amplitude from our equilibrium position down the middle. And we have troughs as the lowest point. So the distance between a crest and a trough is actually 2 times the amplitude of the wave, because the amplitude is the distance from equilibrium. I'll just draw that in so that we remember that all of these distances are measured from our equilibrium. I'll just call it EQM, equilibrium. Next we have our wavelength, represented by the Greek symbol lambda, and that'll always be the distance between 2 identical points on the wave train. So we could measure it from 2 crests, we could just as easily measure it from 2 troughs. That's the same distance as that wavelength. Or we could measure it from this point where our particle is about to begin going down, where it's at equilibrium, and that would be another wavelength. So wavelength is always just between 2 points on the wave that are actually moving synchronously. I don't know if that's a word, in synchronization. So as this point, as the wave travels through it, at this point, it's about to start traveling down as this part of the wave moves over. So this particle is at the crest, about to move down, just as this particle is at the crest right now and just about to move down. So a second ago, this particle was maybe here, and it moved up the crest as the wave moved through it to the right, just as this one a second ago was here, moving up. At this point in time, it's at rest in terms of our vertical distance, and it's about to start moving down. So in a second, that particle will actually be here because our wave will have moved to something that looks like that. That's not a very good drawing, but hopefully you get the idea. So A, again, review, is amplitude, which is also essentially our distance from equilibrium at the maximum point. So similar to simple harmonic motion, except when we're talking about waves, we'll usually refer to it as amplitude rather than distance from or displacement from equilibrium. And that will always indicate the total energy of the wave. So more energy would mean a bigger amplitude. Wavelength is the length of one cycle. So it's kind of related to period, right? As a full cycle goes place, we're going one period of time and one wavelength of distance. So that's a transverse wave. That's our easiest to visualize and to work with, and our ideal type of mechanical wave. Then we have, right, this is where it's hard to visualize on paper, and I really encourage you to watch a video about this. Maybe I'll even try to, I'll post one on the Google Classroom as well. So in a continuous transverse wave, particles move in a direction perpendicular to the wave motion. So the wave itself is moving through this, let's call it our spring that's being oscillated or vibrated up and down. It's going to send waves through it in this direction of motion to the right, whereas the particles themselves, an individual particle on that spring, if we just zoom in and look at this one particle, it's going to actually travel perpendicular to the direction of the wave, up and down, as this wave passes through. Just like this one is going to be traveling up and down. And if we take a look at any one particle, it'll be traveling up and down with simple harmonic motion. That's kind of a key connection for us we need to be able to make. So the particles move in a direction perpendicular for transverse. So remembering that transverse means perpendicular, particle and wave motion, and we have particles that are undergoing simple harmonic motion. So if they're one wavelength apart, they'll move identically. That's another very important note and concept we need to keep track of, and we call that particles that are in phase. So this guy is in phase with this guy, and as it goes down, so will this one, right? And this one is in phase, not with this one, but with this one, because at this point in time, they're moving down with a smaller velocity. So these arrows are all their velocity vectors. So smaller means smaller velocity. This is actually when it's traveling the fastest. And if it's traveling its fastest down, right, those would be in phase. All right, we have transverse, where our particles and our wave are perpendicular. Now we have longitudinal, and this is now parallel. So our source is vibrating left and right, our wave is moving left and right, and our particles are vibrating left and right. Everything moves parallel to the direction of the wave motion. These ones are a little bit harder to visualize. As you can see, this is a little bit of a weirder diagram because these are weirder and harder to work with waves. So this is a compression wave is another way to think about it. And this is actually how sound waves work. So if our source is vibrating molecules on a giant gong vibrating back and forth, those are going to compress the air molecules right next to the gong, and you're going to have a zone of compression. And that zone of compression is going to travel to the right. But in the wake of that zone of compression, we have a zone or a region of rarefaction. So that's almost like creating a little vacuum behind our compressed particles. And it'll continue to have this compression followed by rarefaction regions or high density particles. So in compression we have a lot of air molecules squished together. In rarefaction we have low density where there's only a couple that are more spread out. So you might have the same number of air molecules in this zone as you would in this bigger zone because their densities are different. So same number of total molecules, just in a different volume. And density is all about the relationship of either mass or whatever number of particles we're looking at per volume. Okay, so we still have wavelengths. Instead of peaks and troughs, we have compression and rarefaction zones. And we're remembering that the source vibration and the wave motion is parallel to our vibrating particles. So everything is parallel, whereas transverse, everything is perpendicular. So a sound wave is a common example of a longitudinal wave. It's most realistically represented with a longitudinal wave diagram. We'll often actually convert that to a transverse wave, a representation or a model of a sound wave. So instead of showing zones of compression, we would represent it as a transverse wave with a crest. And as a rarefaction where they're furthest apart would be our trough. So sound waves you'll often actually see represented with these transverse wave models because it does make a lot more sense to our brains and it's just easier to visualize and work with. So this is a realistic wave, sound wave, right? This would be our realistic one. And then our equivalent one would be the sound wave or the transverse wave. All right, some important notes. Due to friction, waves will over time lose their energy, which is represented by our amplitude. So they'll get smaller and smaller crests and troughs with less amplitude over time. So transverse lose amplitude and longitudinal lose density. So that's why when you hear a sound from a kilometer away versus a couple meters away, it's going to be a lot quieter. It has a lot less energy and density to those air molecules. But remember our super important note from lesson 1, frequency will never change. And this is just a weird law. So it'll always continue oscillating with the same frequency. So the source frequency determines the frequency of the wave forever, even if you switch across mediums from air to water or from water to a solid, the frequency will always be the same. All right, and another unique thing, we're all familiar with seeing waves in the ocean, water waves. They're actually not quite longitudinal, not quite transverse. They're circular waves. They have components of both transverse and longitudinal. So if we're analyzing one particle or one rubber ducky sitting on top of this ocean, it's not just going to bob up and down, it's actually going to go in these circles. And there's lots of cool YouTube videos demonstrating this as well. So our particles have this X component, which is the longitudinal, especially when they're closer to the surface of the water. As you get further and further down, you might lose some of that up and down transverse. But at the top we have both a Y component, being our transverse wave, and an x component being our longitudinal wave. And when we get deep enough, we only have our x component. So that would be represented just by a longitudinal wave, like sound waves. All right, important math part with just a little more conceptual stuff before we get into it. We have the speed of a wave. If the medium doesn't change, the speed of the wave is constant. So that's saying as long as our sound wave is traveling through water, right? We don't change the medium from water to air. The speed of the wave is constant. So the only time we can change the speed of a wave is by changing the medium, right? You can change the speed of the wave only by changing the medium, right? So a couple examples of changing a medium would be stretching the spring. So you're actually affecting the medium by stretching the spring. You're moving those molecules further apart from one another, making the metal itself less dense, changing that medium. Different depths of water will also have that. So the medium is actually affected by the density of the molecules. So deeper water is more pressure, right? Higher density, therefore different medium. And even more obvious would be if you were underwater and somebody was talking to you, their voice would sound very different because the wave is traveling different as well. Different speeds anyways. It would take longer to get to you, but the frequency would be the same. And frequency is what determines pitch. So they wouldn't sound higher pitch or anything. It would just take longer to get to you if you were underwater and they were in the air. So frequency and amplitude of the source vibration have no effect on this changing medium. So let's put all of this together into one simple yet elegant equation, the universal wave equation. And this is going to be an important focus for the remainder of Physics 20. So make sure you know where to find this on your formula sheet. You'll memorize it soon enough because the speed of a wave is equal to the frequency of the source vibration, or of the wave because it never changes, times our wavelength. So that'll be kind of key to remember that the frequency doesn't change. Well, our last lesson will throw a little bit of a wrench in that, but as long as nothing is moving relative to one another, frequency never changes. So that frequency should be a constant. Our wavelength can change as we change our mediums though, or we change the speed of the wave. So if we just look at the proportionality of this equation, our wavelength and frequency are inversely proportional. If we divide one side by wavelength, right, we'll have frequency is 1 over wavelength, or V over wavelength. They have an inverse relationship. And if we remember anything about inverse relationships, if one goes up, the other goes down. So if the source frequency is high, that means we have a short wavelength. If the source frequency is low, that means we have a long wavelength, as long as our medium is constant, right? Because as soon as we get a change of medium, we're going to have a change in speed, and that's going to be affecting the inverse relationship of frequency and wavelength. All right, we finally made it to an example. Put some of our universal wave equation skills to the test. So this first one, they're telling us the speed of the wave. No, the distance. So here's our wave. Looks something like that. And it can travel a distance of 120 meters in a time of 4.9 seconds. Back to lesson 1 of all of physics. If we're looking to use our universal wave equation, we need a speed. So speed is distance over time. So we've got 120 meters divided by 4.9 seconds. We get a speed of 24.49 meters per second. So we want to determine the period of the source vibration. Taking a look at the diagram they gave us, this one looks similar to this. 3 different troughs. Actually, it ends at the equilibrium position at a distance of 3.5 meters. They aren't directly telling us the wavelength, but we are able to figure it out with some math. So if we're starting at the equilibrium position, our wave is just about to travel up, right? This wouldn't be a full wavelength. That would be half wavelength because we're beginning to travel down. This would be a full wavelength. So that's one wavelength, right? As we get to here, that's going to be 2 wavelengths. And we end, did I have enough troughs? 1, yes. And then we get half a wavelength. So that's how I like to count my wavelengths. I like to just start and count them out, right? So I have, here's half a wavelength. There's 1 wavelength, there's 2, and a half. We haven't gone back down and up for a full cycle, but we've gone 2.5 wavelengths. You're going to be doing this a lot over our next couple of lessons. So best to get some practice and clarity on that. So from this diagram, we know that 2.5 wavelengths is equal to 3.5 meters. So 2.5 wavelengths is equal to 3.5 meters. That's from our diagram. We'll often have to get information about the wavelength from a diagram like this. It's an important skill. So if we divide both sides by 2.5, we get the wavelength of this. It doesn't even tell us what type of wave it is, but the wavelength of our wave shown in the diagram is 1.4 meters. So now we have speed, the wavelength. We can solve for frequency, and we're looking for period, which is 1 over frequency. So let's rearrange our formula. V is frequency times wavelength. We're solving for frequency, so it will become frequency is equal to our speed divided by wavelength. 24.49, the speed we calculated, divided by our wavelength, 1.4 meters. Take a look at the units. This is our first time working with the wave equation, and this is why it works. We're canceling out our meters. We're left with 1 over seconds, which is a hertz. 1 hertz. I don't know the singular for hertz. 1 hertz, which is frequency. So the frequency of this wave is 17.49 hertz, or 17.49 cycles per second. Not quite done. We need to take our frequency and convert it to period. So we'll do it down here. Period is equal to 1 over frequency is equal to 1 divided by 17.49. And hertz we can convert to our 1 over seconds to see that our units will come out as seconds, which is what period should be in. So we get 5.72 times 10 to the negative 2 seconds per cycle, which is our period and what the question was asking us for. All right, we're not done yet. We have a water wave generator. I'll draw it out. So our water wave generator creates 200 oscillations in 19.1 seconds. So there's a lot of waves. If we're starting at a crest, right, that would be one wavelength. We're looking at a wave that creates 4 successive wave crests, 1, 2, 3, 4, in a distance of 3.8 meters. So we know that this full distance is 3.8 meters. Sorry, 3.85 meters. Messy, messy. And that would be 1, 2, 3 wavelengths, because a wavelength can be our crest-to-crest distance. Those are all particles that are in phase, right? They're at the top and they're about to start going down. All right, so from our diagram that we need to draw, the question doesn't draw it for us. Very important step in all of these wave problems is to draw your wave diagram. We have 3 wavelengths is equal to 3.85 meters. One wavelength would be 3.85 divided by 3. We're trying to isolate for one wavelength. So we get 1.283 meters as our wavelength. And frequency. So in the end, the question wants us to determine the distance. It gives us a time of 24 minutes. In order to find a distance with a time, we need to find the speed. We're going to solve that first. So our first step is to, in order to find speed, we need frequency and wavelength. We have wavelength, we need to find frequency. So frequency is always equal to number of cycles divided by our time. So the question tells us this generator does 200 oscillations or 200 cycles in 19.1 seconds. So we have a frequency of 10.47 hertz. Now we have all that we need to solve for the speed. Excuse me. Allergies. So speed is equal to frequency, 10.47 hertz, times our wavelength, which is 1.283 meters. So since hertz is 1 over seconds, we're multiplying 1 over seconds by meters. We're getting a speed, right? We're getting our answer in meters per second, which in this case is 13.438 meters per second. Now, we're not quite done. We need to work to find the distance that our one wave travels in 24 minutes. So maybe first thing we want to do is convert this to seconds, because we need to work with meters per second compatible units. So 24 times 60 seconds per minute gives us, I don't have that calculated, 1,440 seconds. All right. So using our lesson 1, day 1 formula, speed is distance over time. We're solving for time. Multiply both sides by t, divide by v. We get time is distance over velocity. Sorry, we're looking for distance. What am I doing? We're looking for distance, not time. Distance is v times t. Speed times the time. And our speed of 13.438 meters per second is multiplied by a time of 1440 seconds. That means that that wave is going to travel 1.94 times 10 to the 4 meters, or if you want to convert this to kilometers, we get 19.4 kilometers. Which makes sense. It's traveling pretty fast for a pretty long time. This wave is actually able to travel 19.4 kilometers in that time. Alright, that's all for lesson 5. I will let you get some of that homework done and then encourage you to check out lesson 6 as we work through this last unit. Alright, good luck. Let me know if you have any questions. Hopefully this is making sense even without all of our demos and stuff. Watch the supplementary videos for some better visuals of these waves rather than just pictures and drawings.